Hello, everyone. Welcome to our live session for Wednesday, November 25th in the United States. This is the day before Thanksgiving, and we appreciate everyone joining us. My name is Matthew. I'm one of the instructors for the online classes, and behind the scenes we have Victoria and Alexander. I will hand this over to you, Professor Impey, and we'll get going.
Okay, welcome everyone. Day before a big holiday here in the United States, and we'll just get started right away with your questions.
The first question is from an email. Ruben Riquelme is very interested and amazed by black holes. Could you maybe speculate a little bit about what are some of the kind of craziest possibilities for black holes? Could they connect one side of the universe with the other? Could it be that they would connect multiverses together?
So speculation about black holes, that's a rich subject because we don't fully understand them yet, mostly because we don't have a theory of gravity that unites conventional gravity with quantum effects, and quantum effects are important in black holes. The speculative fringes of black holes do indeed revolve around whether white holes are possible, that is, whether you can have a black hole that interconnects to another part of the universe, a different region of space-time, and so provide essentially a portal in space-time. Since our universe seems to be flat, that's unlikely to happen. That might be possible if the universe had more curvature to it. But that's an active area of investigation. Another speculation around black holes is the fact that inside the black hole, when the black hole is spinning, the solution takes a point source singularity and turns it into a circle, essentially, one-dimensional circle, a circle with no thickness. And in general relativity, that's called a time-like curve. And in principle, if you were able to be inside a black hole, maybe it's a massive one where the tidal forces don't kill you on the way in, you could travel around that time-like curve forward and backward in time at will, potentially meeting past and future versions of yourself. So that's another nice speculation about black holes that does emerge from the gravity theory and from prediction. Another speculation about black holes is really what does happen to the information that falls into a black hole. The community in theory is divided on whether the information is destroyed somehow or whether it's preserved, perhaps at the event horizon in a holographic kind of effect. That's also unclear, and it's part of a speculation about black holes. And probably the final interesting speculation about black holes I'll mention is the possibility of what are called primordial black holes. That is, very small black holes, smaller, of course, than a star, but larger than a subatomic particle, that would have formed from the very dense and knotted regions of space-time close to the Big Bang. And these black holes would indeed evaporate by Hawking mechanism, if that is correct. But some fraction of them, some mass range of them, could survive to the present day. And so these primordial black holes left over from the Big Bang could be a significant component, perhaps, of dark matter. And most of the primordial black hole mass range has been ruled out by observations, but not all of it. So that would be another interesting area to speculate, because they are indeed predicted in some theories of the evolving universe, but have yet to be observed.
The next question is from Reality Fool, who's on with us live. What are your thoughts on the recent Chinese mission to the moon, and what might be found during this mission?
So the Chinese have got a very aggressive and ambitious space program in general. Their number of launches has been increasing steadily through the last decade, and they've had more launches than NASA has for several years now. This Long March 5 rocket that takes their spacecraft to the moon is an extremely powerful rocket. It's fully equivalent in power and thrust and capability to the Saturn V rocket or the Proton booster of the Russians. Those are the two most powerful rockets in the history of the space program. So the Chinese can match that capability, and that'll take them to the moon or Mars if they want to go there. This moon mission is important because it's a sample return mission. First time in, getting on for 50 years that we've brought anything back from the moon. They are also, to be fair to them, because they have a chauvinistic space program in some part, they're willing to share their samples with researchers around the world. So they're not going to keep all the samples to themselves. What's interesting about the place they're going to bring back samples from is that it's a relatively young area of the lunar surface. Most of the Apollo samples came back from very old volcanic shields, so ages of 4 or 3 billion years. The area the Chinese are going to bring back rocks from is about 1 billion years old. 1 billion years ago is about the last time the moon had any significant volcanic or geological activity. And so it'll be very interesting to learn about the lunar surface from these samples and lunar geology at that younger age. We'll give some idea of the history of the moon. Also, age dating these rocks with radioactive techniques will allow astronomers to calibrate their crater counting method, which is how we date planetary surfaces when they don't have atmospheres like Mercury or Mars or the moon. So it's going to be able to be used for multiple purposes. So it's a very important mission.
The next question is from Wendy Traver, who sent an email asking if the universe, the fabric of space-time, is traveling faster than the speed of light and increasing, could it be infinite? And if so, would that require a new model beyond the standard model?
Yes, it could indeed be infinite. So the expanding universe model in its normal form, just given the expansion history we measure with observations, indeed predicts parts of the history where any 2 points in space were moving apart faster than the speed of light. And that means they've receded beyond our horizon. So it's completely conventional part of Big Bang cosmology that there are regions of space-time, physical space, that we haven't seen or can't see because light can't have reached us since then. And if you're asking what the limitation on the model is, there is no limitation. So indeed, it's entirely possible that the part of space-time we see, containing a few 100 billion galaxies, is a very small fraction of the total space-time. And we can't say how large it might be, and it might indeed be infinite. So that's allowed by the model. So it's interesting to know what the limitations of the Big Bang are. The Big Bang doesn't put any outer bound on the size of the universe, just puts a bound in time based on the time till the Big Bang.
The next question is from Mohan46, who's on with us live. Why is the sky dark? Why is the dark sky at night with stars and galaxies? Why are the stars and galaxies equally distributed around the night sky?
So they are not completely equally distributed. The stars, the bright stars you see in the night sky, are more or less equally, or better to say, randomly distributed in the night sky. They can appear to group and cluster. The groupings you see on the sky, unless it's a star cluster, are typically stars at quite different three-dimensional distances, so they're not near each other in space. But they generally are more or less randomly distributed. Now, most of those stars in the night sky are in the vicinity of the sun, within the Milky Way. They're in our corner of the universe, the nearest 1,000 or a few thousand light years. So we're looking at our part of the galaxy. And there is a slight tendency for those stars to concentrate near the plains of the Milky Way. So in that sense, they're not randomly distributed. And the Milky Way itself is showing us that the more distant stars that we can see are very strongly concentrated in a disk-like pattern. So stars are in the very nearby regions of the sun, randomly distributed in three-dimensional space, and on larger scales show the shape of the Milky Way galaxy. Galaxies, which we can't see really with the naked eye, except Andromeda, are not randomly distributed either. They cluster, and surveys really going back 70 or 80 years have shown the galaxies concentrate in large groups and clusters. The Milky Way and Andromeda are part of a small group called the Local Group, which also includes a few dozen dwarf galaxies and the large and small Magellanic Clouds. So galaxies are not randomly distributed either. They show the imprint of gravity into forming structures like clusters that are large, that could be 50 or 100 million years across, and could contain thousands of galaxies.
All right, and kind of a follow-up, and I think I may have misunderstood the question the first time. So with this distribution of galaxies and stars all around us, why is the sky dark at night?
So the question of why the sky is dark is an interesting one, and it's called Olber's paradox. Olber was a German astronomer in the early 19th century, but actually the idea predates Olbert, so it shouldn't really be given his name, since a number of astronomers before him talked about it. It's the idea that if you lived in an infinite universe, logically, in any direction, eventually you'll hit a point of light. And since the light we receive from an object, whether it's a star or a galaxy, goes down as the square of the distance, and the number of galaxies or stars at any particular distance is the surface area of a sphere, which goes up as the square of the distance, the light from each star or galaxy goes down at exactly the same rate as the number of stars or galaxies is increasing. And that implies, and you can show the math of this fairly easily, that in any successive shell going out in the universe contributes an equal amount of light. And so if the universe is infinite, adding those shells of light produces infinite light. And so that's the logic by which in an infinite universe, the night sky should be bright. Now, in stars, it isn't bright because we know we live in a finite system of stars called the Milky Way, and we can already see to the edge of that galaxy. So starlight is not going to fill the universe because the stellar system we're in has a finite number of stars and there are large gaps of space to the next stellar system. But galaxies, of course, are distributed on much larger volumes, and there are hundreds of millions, hundreds of billions of galaxies. And so it's a real question as to why the sky isn't bright from distant galaxy light. And the answer is because we live in an expanding universe. So the redshift causes a reduction in energy, or light intensity, if you like, of a more distant galaxy. So the galaxy light does not increase as you would expect it to in that naive calculation. Also, there's a finite time in the age of the universe for light to have filled the space between galaxies. And so the universe is not, therefore, uniformly bright. So the expanding universe and the redshift are the primary reason why that's the case.
Excellent, thank you. The next question is from David Learning, who's on with us live. How is astronomy or astrobiology research being applied to mitigate the climate crisis?
Astronomy per se doesn't have a direct relationship to the climate crisis, but the study of astrobiology and how life interacts with a geological environment or an astronomical planetary environment is informing us somewhat about climate change, because it's telling us how planets regulate themselves in terms of their temperature. The mechanism, for example, of the greenhouse effect was first noted, and it essentially made him famous, by Carl Sagan back in the 1960s and 70s. And he was basing his arguments on Venus, which we think suffered a severe greenhouse effect. And obviously, we have a big lesson to learn about the greenhouse effect from Venus because we're experiencing a version of that on the Earth. So that's a dramatic example of how understanding how planetary atmospheres work can inform our understanding of our own atmosphere. Also, astronomical observations have also informed us about the relationship in the energy flow between atmospheres, oceans, and the land surface. That's also relevant to climate change because on the Earth, we've learned that about 90% of the heat capacity of the planet is in the oceans rather than the atmosphere. The atmosphere tends to radiate its heat out into space or deposit its heat back into the oceans or the ground. The reservoir of heat, and then essentially the engine of heat that drives the climate, are the oceans of the Earth. And so astronomy research was important in understanding that. Those are the two main ways. It's better to get a planetary type perspective on our own planet with all its various mechanisms to understand the role of climate and the future of our climate.
The next question is from Paula Stiles. And Paula, we're not going to get super political, but I do think it's fair to ask, how do you think that the next administration might change or continue NASA projects and policies and private space programs? Can you talk about what NASA's sort of priorities are and how you think they might stay the same or change in the future?
Right. I mean, the general comment I'll make, without being political at all really, is just the reality of the fact that the NASA administrator is a political appointee. And so NASA's ability to do long-term planning is subject to what we would call the political cycle, which is typically a 4-year presidential cycle. But of course, Congress changes every 2 years. So the political cycle can be even shorter than 4 years. And this is a real limitation on planning. The other federal agencies, such as the National Institutes of Health and the National Science Foundation, they tend to have directors in place for quite long periods of time and more stability in their policies. NASA has been a political football because its programs are expensive, they're high profile, and there are programs that a lot of people and constituencies care about. So it's been difficult historically for NASA to stay above the political fray. And the problem has typically been that they just can't do long-term planning because a new administration comes in and may change things. The successor to the space shuttle was a classic example of that. The successor to the space shuttle was planned a couple of decades ago, well before the last shuttle launched about 10 years ago. And it was reincarnated several different ways. It was canceled and reinstated by successive administrations and still doesn't have a forward plan. And in the meantime, we've watched the private space industry take off and Elon Musk succeed with SpaceX in sending astronauts to the space station just a week or so ago. So this is the limitation of NASA in a political environment. It's not that the programs it does are politicized so much as the fact that there are political pressures on their programs. I think the most overt political pressure in the last 4 or so years, the last administration, has been the fact that NASA does significant amount of climate science. It supports Earth observing telescopes and Earth observing satellites to monitor the Earth's climate. And that research has really been squeezed and squashed by the last administration. So that will probably change, of course, with the next administration. Otherwise, in terms of space propulsion systems and going to the moon and Mars and so on, these have been subject to fluctuating fortunes for decades. And so it's not going to change as long as there's political pressure and the administrator is primarily a political appointee.
The next question is from Ayush Singh 26. Recently, I read that scientists are able to detect neutrinos from the CNO cycle of the sun. Can you please explain what is so special about neutrinos and why are they so difficult to detect and are they harmful?
So neutrinos are very fundamental particles. They're on a par with electrons, protons, and neutrons. They're almost massless, but not completely. We understand they do oscillations, and so they must have a mass, but that actual mass has not been measured. They come in different flavors or families. There are electron neutrinos, muon neutrinos, and tau neutrinos, which have counterpart particles of the electron, the muon, and the tau particle. And so these three flavors of neutrino can oscillate. A neutrino can turn from one into the other. In every fusion reaction in the sun, whether it's the proton chain or the CNO cycle, the two main energy production mechanisms in the sun, neutrinos or antineutrinos are a byproduct. And so they're emitted and they flee the sun without interacting and are available to be detected on the Earth. So we've been trying to detect solar neutrinos for 40 years. And the deficit of solar neutrinos was first seen way back in the 1960s. So neutrino observations are very important in understanding stellar fusion processes. And the CNO cycle is a good example of that. Determining the spectrum of neutrino energies from the sun is a very important constraint on understanding the CNO cycle. These are typically deep mine experiments to detect the neutrinos and their oscillations. And they've been pretty successful over the last decade. And of course, if we can't understand the fusion process of the very nearest star to us, there's very little chance that we can understand well the fusion that occurs in more distant stars. You may have muted yourself.
My apologies. The next question is from Texadactyl. In the LHC, when two protons collide, what are the other products in addition to the Higgs boson?
In the LHC, the Higgs boson is really not a primary product of the collision of protons and antiprotons. It's actually a very secondary evanescent product. The primary product of these collisions is that the energy in the rest frame of the particles goes into creating any particle that's within that amount of energy divided by c squared. That gives you the mass of particle or antiparticle you can create in a collision. So when the particles in the LHC collide at their maximum energy of TeV, tera-electron volts, a whole slew of particles are produced. Sort of a spaghetti of particles that emerge from the interactions. They pass through magnetic fields, so the charged ones are curved in their trajectory, and you can see whether particles were positively or negatively charged. And then they plow into detectors like scintillator sheets or gas chambers or other ways that the particles deposit their energy and are being detected. So the Higgs particle, the Higgs boson, was detected by a very indirect mechanism where particles created from the collision produced decay products, which in turn created an evanescent or very transient signature that indicated the Higgs boson. The Higgs boson was not created and liberated and then trapped in a detector. It was far more subtle than that. It was a resonance at a particular energy in a secondary interaction that indicated the Higgs. So this was a very difficult experiment. Now, when that collision occurs, there are many other particles created and many other decay products from those particles. So there's plenty of things to look at in a collision at CERN apart from looking for the Higgs.
The next question comes from a couple of different people. Single Coded and Parseval Fusto both have asked, I guess recently there was news about an ancient fossil galaxy that has been discovered within our Milky Way. And can you talk a little bit about what that discovery was about and what that means to find a fossil galaxy within our own?
Right. The theory of galaxy formation and evolution fairly confidently asserts that galaxies are constructed from collisions and mergers over cosmic time, and so built up from small pieces. And so early in the universe, 1 billion years after the Big Bang or so, the first galaxies were dwarf galaxies. Those dwarf galaxies merged. Some of them also grew by accreting gas, so they don't simply grow by mergers, but by acquisition of raw material for making new stars. And over billions of years, they gradually merged to form the large, fully fledged spiral galaxies and elliptical galaxies we see around us. So we think this process continues. It's much slower than it used to be because the universe is, of course, expanding and so is less dense, and the odds of interaction or merger is going down with time. But we can see evidence right now that the Milky Way has merged some dwarf galaxies, recently ingested dwarf galaxies, and is in the process of merging with some dwarf galaxies in the neighborhood, and in the future they will fully merge with the Milky Way. So these fossilized galaxies are essentially the ripped apart remnants of a dwarf galaxy, typically sort of shredded or torn into a tidal stream of stars. So you look for a stream of stars using spectroscopy. You don't see a real galaxy here. You're looking at individual star patterns to discern that a galaxy has been shredded as it falls into the Milky Way. And more than a few of these have now been seen. So these ghost galaxies that were part of previous mergers into the Milky Way have been seen. And occasionally you find one, and there are a couple, which seem to be in the act of falling into the Milky Way. So this merger and building process, we know it happens now because we can catch galaxies in the act. So it's a very important part of our story of how galaxies form and evolve. The Magellanic Clouds, for example, are nearby neighbors to the Milky Way, and there's a stream of gas that's been pulled off the Large Magellanic Cloud called the Magellanic Stream, visible with radio telescopes because it's cold gas, and that's another evidence of interaction between us and one of our neighbor galaxies.
The next question is from Ricardo Costa Silva. The new net of satellites, I'm assuming this is referring to Starlink and other big constellations of satellites, creates several issues in observational astronomy from the Earth. Do you think that developments like this will increase the investment in new observatories to be located outside of Earth orbit? And is it feasible to have such a tool on the moon?
Yes, it's not a cheap solution, though. I mean, we have these large telescopes. The facility most heavily impacted by the constellation satellite arrays is the Large Synoptic Survey Telescope, renamed last year to the Vera Rubin Observatory. So it's a huge mirror, 6.5 meter mirror made at our mirror lab, doing survey science. And the sky brightness caused by these satellites is going to put streaks across almost every image this telescope takes, and occasionally make some of them unusable. So this is a problem. And it's true for all these very sensitive survey type telescopes. They're going to see these trails, especially just after sunset and just before sunrise. There's no easy solution. Astronomers are negotiating with the companies like SpaceX to coat the satellites with very matte black paint so they reflect less light, or make them smaller physically. It's unclear how successful they will be. The alternative, yes, there are darker, more stably dark places beyond Earth, but they're very expensive to put telescopes. The unilluminated side of the moon is probably the best of all because it's truly dark. But to put the infrastructure there in place to build a telescope robotically and then operate it robotically is beyond our capabilities at the moment. Maybe in 10 years we could do that. And I think a number of astronomers would want to do that, for not just for the constellation satellites, but just because dark areas of the moon are very, very good places for optical observatories.
The next question is from Federico Subikursky. How much math or how much maths is needed to understand and verify the arguments first of Ptolemy and then those of Copernicus, Kepler, and Galileo? Is it enough to know Euclidean geometry? Do you need more advanced mathematics to understand those?
Up until the era of Kepler and Galileo, yes, geometry, simple Euclidean geometry is actually quite sufficient, and you would need some algebra too. So I would say those two tools are sufficient. Some of the geometric calculations can be complicated, but it is still basic geometry. By the time you get to the era of Galileo and then of course Newton, you're into the reign of calculus. And so at some point, to understand how objects move in space, you actually need calculus. But you can also do a lot of astronomy without calculus. So I would just point that out, that positional astronomy doesn't depend on calculus.
Excellent, thank you very much. The next question is from one of our live viewers. It's about Newton's law of gravity. It's used by NASA for spacecraft landing and other activities, and yet it is not considered complete as far as general relativity is concerned. Let's see, which describes gravity in another way? Which one of the theories is most accurate, and which do we use for spacecraft mostly?
The general theory of relativity is more accurate. It's a superset of Newtonian gravity. In other words, when the gravity is weak, Newton's theory does extremely well and is very precise. When the gravity is strong, you have to go to general relativity. But in the weak field limit, if you like, general relativity reduces to Newtonian gravity. So that sort of answers the question that we only need general relativity when the gravity is strong. And that's, of course, in the situation of a black hole, a neutron star, maybe a white dwarf, or the universe as a whole. However, for purposes of spaceflight, telemetry, sending planetary probes, getting to the moon, all of these things, Newtonian gravity is perfectly sufficient. None of the gravity fields in the solar system are strong enough that you need general relativity in the calculation. And so NASA uses Newton's law almost entirely.
Excellent, thank you. The next question is from one of our live viewers, CS Unz. You mentioned in some of the videos in our classes that you've had some interesting and pretty great opportunities, like visiting the observatory in Rome. What would you say is one of the coolest experiences that you've had in your astronomy career?
I'm going to answer that, but I'm going to put in a postscript on my previous answer to the question about what gravity theory is used in by NASA. So I'll make one big exception to that, and it's an important one. That for sending rockets around the solar system and space probes, absolutely Newton's law of gravity is sufficient. However, in situations where you need extremely accurate timing and positioning measurements, you actually do have to use general relativity, because even in the weak gravity of the Earth, general relativity does apply, of course. It's just that its effects are very subtle and weak. And so indeed, general relativity was tested by observations in Earth orbit of the Gravity Probe B satellite. And the other important example, of course, is the GPS tool that essentially everyone on Earth with a cell phone uses to say where they are. For GPS to work with an accuracy of a few meters or a meter, you actually have to have extremely accurate timing of signals from Earth, from a network of Earth satellites. And the level of that timing precision is such that you need general relativity in the calculation. And so these things, and essentially GPS on your phone, GPS that most of us use every day of our lives, would not be possible if you didn't use general relativity in the calculation. As for fun and exciting and exotic and bizarre and interesting experiences I've had in astronomy, well, I've had a lot because I've been observing and an astronomer for a long time. Some of them, I'm not going to, talk a lot of stories, though I could. Maybe one of the more interesting sets of experiences I had was in 3 visits to the Russian 6-meter telescope in the Crimea. I had never been to Russia the first time I went there, and the first time I went there was just on the eve of the revolution that toppled the old regime and put Boris Yeltsin in power as prime minister. And I literally arrived in Moscow not knowing that that was happening, and walked around the corner from my hotel to the center of the city and saw the Parliament building in flames and tanks surrounding it and people in the streets, and then went off to observe. So that was a pretty interesting trip at a very pivotal moment in history. Observing in Russia was interesting too, because it was a contrast between the incredible dedication and high-level training of the Russian scientists I was working with and engineers, very well trained in physics, mathematics, really smart people, and the dire conditions under which they worked. A senior staff scientist at the Russian National Observatory in Crimea would be paid back then equivalent of about $30 or $40 a month, and they just lived hand to mouth. They had to, forage for wild mushrooms and wild fruits and vegetables on the hillsides in the Crimea. They could barely get enough money for food. If they had kids, they were immediately planning when their kids were young to send them overseas to get educated. The infrastructure was frail, things were falling apart. It was a kind of a sad place, actually. Now, Russia has changed since then. Maybe it's got better in some ways, and maybe not. There was a huge brain drain. But just observing in Russia gave me so many insights that were well beyond astronomy into the culture of science. A sort of very proud scientific country. It's made enormous contributions to many fields of science, physics especially, but also astronomy. And then to see what it was like on the ground for those scientists, that's the kind of experience that makes you appreciate where you work, where you live, the tools you have, the resources you have, the salary you have, and so on. So if I were going to pick one story, I would tell that story.
The next question is from an email. Horacio Sarabrinsky asks, I do not really understand what it means for information to be lost inside of a black hole. Could you provide some examples that might help illustrate it?
Sure. I'll give a trivial example and then a more deep physical example. The trivial example is if you just were near a black hole and you tossed books or an encyclopedia into the black hole, you just lost information. That information was available to you to read outside the black hole, and as soon as you toss it in the black hole, even if the book is not destroyed, the information is unavailable to you. So you can literally lose information in a black hole. Now, in a physics sense, there's another way to put this. The definition of information, which is related to the definition of entropy, is the number of equivalent microscopic states. And so that's a physics type idea. But in terms of a black hole, what that means is when you have a black hole, the black hole tells you nothing by observing it about what processes went on to produce that black hole. You don't know, for example, if one single massive star just died and its core collapsed to produce the black hole, or if perhaps a series of stars collided and merged and between them got big enough to become a black hole. Those are very different scenarios, but the black hole is mute to how it was made. And so that's a more physics-based way of thinking that information is lost. The entire formation scenario before the event horizon, what went into it, is lost. And you can imagine any number of other scenarios that could have led to a black hole that you cannot learn by looking at the black hole. So information is definitely lost. The argument remains in the physics community over whether somehow that information is preserved at the event horizon in a way that perhaps could be read out some way, as a hologram is read out. That's a controversial idea, and nobody has figured out a way to make it practical. So at the moment, it's just speculation.
The next question is from P. Stapleton, who would like to know if you can discuss a bit about the notion of how much time is available but also required for intelligent life to evolve. In our case, it took a few billion years. But since the universe is so much older than our solar system, does it leave the possibility that intelligent life has evolved before our solar system and it has come and already gone?
So to answer the last part of the question, absolutely. There's enough time in the history of the universe for Earth clones, that is to say, twins of our Earth with all the conditions needed for life, to have got their start 7 or 8 billion years before the Earth got its start. So however long it took on Earth, and of course it took, roughly 4 billion years to go from the very first forms of life to intelligent species with technology like us, you have more than twice that amount of time before the Earth even formed for that to happen elsewhere. So absolutely, there's a possibility of it happening elsewhere and reaching a much more advanced state. The question of how long it takes in general, beyond the example of the Earth, for intelligent life to evolve is highly controversial, because you can argue both sides of this. The general feeling, based on what we see in our own history, is that it takes a long time. Because if we think about it, life first started 4 billion years ago, and you could come back onto the Earth for the first 90% of its history until about 500 million years ago and find no form of life larger than the head of a pin. All life was microscopic, and there were various bacterial colonies, but that was it. So the entire evolution of life towards larger forms and forms that have intelligence eventually is concentrated in the last 10% of that history. So it took a long time. 3 or so billion years, and you might imagine that it could take longer than that, or maybe it can be shorter than that. We simply don't know. And even then, that's not the question of brains. The evolution of brains was a slow process. It started with nerve cells and nerve endings and sensory apparatus on creatures in the oceans that gradually turned into sensing devices such as heat sensors, because fish have sensing of heat, or magnetic fields, or of course eyes. And eventually the information that organisms were capturing requires some processing. So you have the development in vertebrates of a nervous system, a central nervous system, and a central processor to deal with that information, and that turns into a brain. But this evolution takes hundreds of millions of years to form the first rudimentary and very, very small brains in creatures in the oceans. So it takes a long time for brains to evolve on the Earth, billions of years after life has started. And these are the timelines by which some people say it does take a long time. But that's not to say that it has to take a long time. That's a dangerous argument to make based on a sample of one. So others have argued that if you had 100 Earth clones getting their start under 100 identical stars, maybe on some of them intelligence would never happen. And maybe on some of them it would take as long as it did on the Earth, and maybe on some of them it would happen quicker. We simply don't know.
The next question is from Full Bear, who is on with us live. As an amateur astronomer, I was wondering if there is a method or tool that can be used to measure parallax for determining which targets are closer or further away.
Parallax is it's a fundamental measuring method for astronomy. It's not so much a question of the telescope, it's a question of methodology of how you do it. To measure parallax the simplest way, you actually have to make identical observations of an identical object with the same equipment, same telescope, from different parts of the Earth's surface where you know the distance between. And then you can set up a triangle, essentially, with its apex angle out in the sky between the 2 points you're observing from. And that allows you to calculate a parallax angle and get a distance directly. It's not that that can't be done by amateur astronomers, but the requirements of precision of measuring time and separation of two locations is more fundamental and more challenging than actually having a telescope that can measure the angle of the objects in the sky at any given time. So that's essentially why parallax is not a typical measurement done by amateur astronomers.
The next question is from Leo Prince August. The question is simply, can you please tell us about warp? I'm assuming they mean, some kind of warp drive, but can you talk about, warping of space-time, either, something that we could do for travel or just in general, possibly in the case of gravitational waves?
Right. So I'll answer that as sort of two questions in two different ways. The meaning of the word warp in terms of space-time is well understood by general relativity. So general relativity equates the curvature of space-time with the amount of mass and energy density at any location. And so it's fundamental to general relativity that space-time can be curved by mass and energy, and that, if you like, is warping space-time. And we've seen this many times. The best way to see it is in any of the pictures of gravitational lensing taken by the Hubble Space Telescope. That's where light from distant galaxies is bent around an intervening mass distribution, like a cluster of galaxies, producing little arcs of radiation for the distant galaxies. So it's a perfect example of the warping of space-time. And there are many other examples. So that's pretty standard general relativity. It's been confirmed now for 100 years. The other sense of the word warp, of course, is traditionally in terms of warp drive, which would be a superluminal mechanism for traveling faster than light. And that essentially is not possible by the laws of physics. There was a flurry of interest in Alcubierre drives, which was a very speculative theoretical paper about how you could get faster than light. Propulsion or tachyonic drives is another way to put it. There are no obvious basic physics mistakes in those papers and that calculation, but most people just think this is not a viable technology because it's based on physics that's really not observed in the lab. So we've never observed tachyons. We've never observed particles traveling faster than light. Light does appear to be an ultimate limit in physics. It's built into physics, built into special relativity. And so no one anticipates that a warp drive is possible unless there's some physics that we've been totally missing, which is always possible.
The next question is from an email. How do astronomers know if a comet's origin is the Oort cloud or Kuiper belt? And how do they determine if a comet is a returning comet or a new one, given the difficulty of tracking over such great distances?
Well, there are several ways you might be able to distinguish. For instance, if the trajectory of the comet is coming in at a large angle to the ecliptic, then it has to be an Oort cloud comet because the Kuiper belt lies in the plane of the solar system. So when you see an incoming trajectory at some angle from the ecliptic beyond 5 or 10 degrees, then pretty much has to be an Oort cloud comet. However, if you see a trajectory from in close to the ecliptic, it could be either one. So that doesn't distinguish it. The velocity also perhaps tells you something because the Oort cloud is a repository of comets that exist at very large distances, on average 50 to 100,000 astronomical units. And if you look at the Keplerian motion of such an object, you can predict what its typical velocities should be when it's close to the sun or the Earth. And so these tend to be very high velocities. So velocity can also tell you whether you're looking at an Oort cloud comet on a periodic trajectory or a Kuiper belt comet that may not be on a periodic trajectory. It may have been just dislodged or gravitationally influenced out of the Kuiper belt and be heading on an Earth-crossing trajectory. So there are a few clues like that. It would be nice if there were also geological clues by spectroscopy telling you the kind of rock and ice that the object is made of, but we don't have sufficient understanding of how these sets of objects form to make that distinction.
The next question is from Mariana Kovalchuk, who's on with us live. Can you share your thoughts on the new James Webb Space Telescope? What are the main goals for it, and what areas in the universe can it possibly shed light on?
The James Webb Space Telescope is the successor to the Hubble Space Telescope. It's been long in coming. It's heavily over budget and heavily delayed. It's supposed to go up in October next year, 2021. It was close to being canceled several times by Congress, who got exasperated at the way it had blown through its budget limits. And I don't even know what the best guess is what its eventual cost will be, but it's upwards of $10 billion, I think. It's a successor to the Hubble, but it's significantly different because it's a telescope optimized to work in the near infrared rather than visual range. And that's because it's a very large telescope, and it was not possible to get precision imaging at short wavelengths, which is more demanding of the telescope mirror surface. This is a telescope where the petals or the pieces of a telescope will unfurl in orbit because it's too big to launch as a full telescope, 6.5 meters. And that's a very challenging mechanism, which scientists are worried about whether it'll work correctly, because this object, this telescope, is of course sitting at a Lagrange point. It's not in Earth orbit at all. It's far from the Earth and not serviceable by astronauts. So essentially has to work out of the box. Its main science is going to be looking at first light, the first wave of star and galaxy formation in the universe within a few 100 million years of the Big Bang. It's going to do important work on exoplanets, on characterizing exoplanets in the near infrared, their atmospheres, hopefully. Maybe looking at life signs on some of them through their atmospheric signature. It's going to do important work on dark energy and dark matter, little experiments that'll hope to tease out more properties of dark matter and dark energy. And it's, of course, going to do, the usual deep cosmology work of looking for faint galaxies and how they cluster and how they evolve and so on. Well, it will be doing science across the full portfolio of astronomy.
So the next question is from an email. What if large planets like Saturn or Jupiter didn't have moons? Would the planets still be in the same orbit? Like, how would it affect them if they, if those, some of them with many or large moons didn't have them?
It really wouldn't affect them much at all, because you have to remember that just as the planets all put together are some tiny fraction of the solar system mass, less than 0.1%, so the moons of the giant planets, if you sweep them all up, are a very small fraction, I think less than 1% of the mass of the giant planets. So that's the easy way to say that they don't really influence the situation that much at all, because they're very small mass. They're essentially formed from the residue left over from the formation of the planet. And that planet formation process is fairly efficient. Sweeps up most of the material, so there's not much left to make moons.
One of our live viewers would like to know if you have, do you know if there are any new ideas about the 1977 WOW signal that was detected by radio telescopes? And what are your thoughts on the possibility of extraterrestrial intelligence?
Okay, I'll address the WOW signal as one question and the second question separately. The WOW signal is famous in the history of astronomy from 1977, I think. It was a detection at the Ohio State Radio Observatory. This is an array telescope situated, I think, in a football field at the Ohio State campus. It's since been deconstructed, but it worked for several decades doing basic radio astronomy, but it was also sensitive enough to look potentially for signals from elsewhere, from distant stars of artificial origin. Stars should not emit radio waves. So when you see radio waves coming apparently from a star, that's a sign of something interesting. The WOW signal was written on a strip chart, so in the old style of observing back in the 60s and 70s, radio signals or other non-optical signals were converted into an electrical signal which drove a pen on a strip chart on graph paper and showed the strength of the signal. And so in this observing, one of the operators at night saw this booming signal that made a great radio pulse and then disappeared. And he wrote "wow" by the signal exclamation mark and brought it to the attention of the observatory. They tried to look at that same piece of sky the same night, the same direction and the same time the following evenings, and never saw the signal repeat. And people have looked at that piece of sky at other times with other telescopes and have never seen any strong signal. So unfortunately, when you have a one-off signal like that, you just have to view it as an anomaly. You can't really legitimately claim it as an extraterrestrial signal that's jumping to way too many conclusions. And so the WOW signal just sits there as an unverified signal. Now, as to the second question of whether, what I think the likelihood of ETI as extraterrestrial intelligence, I think statistically it's quite likely, because we now know there are, just from news stories that put a number on it in the last few weeks, 300 million habitable worlds or Earth-like planets in just the Milky Way galaxy. And so life on any one of those habitable planets might have time to evolve to intelligence and technology and use our kind of methods to either explore the universe, travel through the universe, or send signals out into space, artificial signals of light or radio waves or X-rays or who knows what. So I think that's entirely plausible that that could have happened. It's just incredibly hard, basically impossible, to put a number on the probability of it happening elsewhere, even though it happened here. So the odds of it happening somewhere are, of course, 100%, because it happened here. Knowing the odds of whether it happened anywhere else is not possible to estimate right now.
The next question is from Ayush, who would like to know, I recently heard that astronomers detected the shadow of black holes. Could you give us an idea about what is the significance of the shadow of a black hole?
Sure. The shadow is the fact that the event horizon is the region of a black hole from which light cannot escape, nor any other information, no particle, no photon, no radiation, nothing can escape from a black hole. So if that black hole, therefore, that the event horizon, therefore, is an obstacle, it's sort of light cannot escape from it and light cannot pass through it. And so it acts as if it's a physical object in a sense, and so it can create a shadow on illuminated gas or bright gas behind it. Now, it's not as simple as a shadow, because shadows on the Earth travel in straight lines. You just project the rays of light past an obstacle, and you can see what the shape of the shadow is. With a black hole, the light is being bent by gravity, so the shape of a shadow is not at all trivial when you're close to a black hole, because the light is being bent as well as obstructed. And so the black hole shadows in models are quite convoluted and complicated. And indeed, the M87 shadow of it was consistent with the calculation in general relativity when it was published a few years ago.
The next question is, if light does not have mass, then why is it affected by a black hole?
Light doesn't have mass, but light is considered to travel in packets of energy called photons. And a photon is a discrete packet of energy, analogous to a bullet or a projectile, tiny projectile. And by E equals mc squared, any packet of energy has an equivalent mass. Just divide the energy by c squared, and that's its equivalent mass. So you can equally well conceive of a wave of light with a certain energy as being a photon of light with a certain equivalent mass. And it will therefore deviate according to general relativity in its trajectory, just as any mass would.
Another one of our live participants, RLL or RIISB, says that they just read an article hypothesizing that information has mass and proposed an experiment to measure that mass. Have you heard of that? Do you have any comments on how something like that might work?
I'm not sure of that particular experiment, but the general principle, I think, must be correct. We don't tend to think of information as being a physical entity. It's just a way of classifying something in binary computer parlance. It's a string of ones and zeros. However, in practice, if you want to transmit information in the universe, down a wire, anywhere, you are actually also transmitting energy. So there's no information transmitted without also transmitting energy. And in that sense, you can make an equivalent mass. So I guess you can always calculate some equivalent mass or mass associated with information, because information implicitly involves the transmission of energy at some level.
The next question is from C. Sunts 1234, who says they are someone who is just entering the astronomy field and they're trying to gauge which area to specialize in. So I think everybody would be interested in the answer to this. So what are some up and coming areas of space astronomy, aka ones that will most likely receive funding?
Mm-hmm. Well, that's getting easier to say given the last 5 or 10 years. So the traditional areas of astronomy divide into study of planets. Planetary science almost is its own field, but study of planets in the solar system, study of stars, study of the Milky Way as a whole, our galaxy, study of galaxies beyond the Milky Way, and the study of the universe as a whole, or cosmology. Those are roughly 5 different fields of astronomy. I would say in the last 20 years, there's been an increasing interest in the study of galaxies and cosmology, and you can measure this in terms of the fraction of time awarded on the Hubble Space Telescope over several decades, or other large telescopes. So this is a quantifiable thing at the level of research. In terms of what is getting more time now, some of the niches of astronomy are really booming. A niche that's booming, of course, is astrobiology, which is the study in large part of exoplanets or the history of life on Earth. Those are both doing very well. Cosmology is a big subject, but it's still growing rapidly, still attracting a lot of interest, a lot of funding. And then other areas that are growing are, of course, the study of gravitational waves, which is related to gravity theory and general relativity. That's also very rapidly growing because it's a brand new field of science. So those are fields that I would say you could put a bet on for the future.
All right, it is now 2:01, so I think this will be our final question for today. Single-Coded commented, a while ago I was watching some videos about the Vatican astronomical observatories and was amazed at the activity that the Vatican had done in the field, including recent construction of their own observatory in Arizona, if I recall. Mm-hmm. Do you think that current discoveries in astronomy could end up having an influence on certain aspects of how faith and religion evolve in the distant future?
That's a good question. I'm very familiar with this because the Vatican Observatory has a research station right here. They have a telescope on Mount Graham, south of us, in University of Arizona. They have a research office in my building, and I know all the Vatican astronomers, all the Jesuit priests who are astronomers, and they've been doing research for, serious astronomical research with us for 40 years, and then within the Vatican for actually 150 years, since the mid-19th century. So there's a long tradition there of Jesuits doing astronomy, and it's sanctioned at the highest level of the church. The current Pope, Francis, is a Jesuit, and he's very supportive of science. It grew most strongly under John Paul II, who helped fund the telescope that they built in Arizona. So it's had pretty strong support from popes throughout the last half century. In terms of the future of the relationship between science and religion, I think it's an important marker because some parts of the world and some sectors of the United States population feel that science and religion are in conflict. I don't think that's necessarily the case or has to be the case. And the Jesuits' practice of astronomy and their collaboration with scientists over half a century is a pretty strong counterexample of why they don't have to be in conflict. It would be nice to see maybe more examples of this. But I think if you're going to talk about the future, I think there's, as long as people are, tolerant in every way you can imagine the definition of that word, there's no reason scientists and religious scholars or practitioners of religion shouldn't be talking to each other and collaborating with each other, even for the long term. So that was an interesting question to finish with, an unusual one. And thanks again for your questions on a variety of topics. It's holidays for us. We'll be back with you next week and the week after and announce the next 2 dates. So thanks for Vicky for running behind the scenes, Alexander for saving our bacon as he always does when we have something that goes wrong or a glitch, and Matthew for facilitating the conversation. Okay, bye everyone.
All right, and we will try and post the stream. We have to wait 24 hours before we can put it up on YouTube, but we try to get it up soon after that. So we'll try to have this up probably sometime on Friday. So thanks everyone for joining us.